There is this very specific moment when you're learning to code. Maybe you've picked up some Python, you've written a handful of SQL queries, and you think, okay, I am finally ready to build artificial intelligence.
Right. Yeah, that classic pivot.
Exactly. But the reality is, making that shift from just writing code to actually thinking like a machine learning engineer, well, it's a massive leap. Because in real production level ML systems, you don't just sit down and start from scratch with a blank screen. You start from a playbook.
Precisely. I mean, the difference between an amateur trying to build a model and a professional deploying one, it isn't just the syntax they've memorized, it is the systemic frameworks they use. You approach a problem before you even type a single line of code. You don't guess what might work. You apply proven patterns.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects. Today, our mission for this deep dive is to unpack what our sources call the feature engineering playbook. We are going to master the 10 foundational SQL patterns that are actually used in real machine learning systems.
And to really grasp those 10 patterns, we first have to redefine what feature engineering actually means, because a lot of developers coming from traditional software engineering hear that term, and they just assume it means cleaning up messy data.
Like handling missing values or standardizing dates, that sort of thing.
Yeah, exactly. But a much more accurate mental model for you to have is this feature engineering is designing signals.
Designing signals.
Yeah.
Okay, walk us through how that differs from just preparing data.
Think about it like a restaurant. Machine learning models do not eat raw data. If you just dump a truckload of raw ingredients like flour, sugar, raw eggs onto a dining table, you can't serve that to a guest.
No, definitely not.
Right. And in our world, that raw ingredient is your transactional data. Every click, every timestamp, every user ID. Models eat prepared dishes, and those dishes are called features. You are taking raw ingredients and combining them to highlight a specific human behavior. You're designing a clear mathematical signal that the algorithm can actually digest and learn from.
So we aren't just handing the algorithm a giant database table of, every time a user opened an app. We're cooking that raw data down into a specific metric that tells a story.
Exactly.
And according to the playbook we're looking at today, every single feature we create is basically trying to answer one of three core questions, right?
Right. If you strip away all the complex SQL joins and the advanced math, every feature answers what happened, which tells the model about user behavior. When did it happen? Which tells the model about time. Or how is it changing? Which tells the model about the trend. Behavior, time, and trend. That is the entire playbook framework right there.
Behavior, time, and trend. Having that three-pillar framework really keeps you from drowning in data overload. So before we get into the advanced transformations, the playbook lays out the industry-standard baseline for ML features. They call it the RFM trio, which covers the first 3 patterns in our 10-pattern list.
Yeah, the RFM trio. It stands for recency, frequency, and monetary value. If you are building a churn prediction model or trying to segment your customer base, or even writing the foundation of a recommendation system, this is always where you start. It's the absolute bedrock of behavioral modeling.
Let's break those down. So pattern 1 is recency. The core question is simply, how recently did the user act? And if you are writing the SQL for this, the translation is usually a function like datedef. You're taking today's date and subtracting the exact date of the user's last logged activity.
And the reason models care so deeply about that specific difference in days is that human behavior is incredibly time sensitive. I mean, a user who logged into your e-commerce app yesterday is in a completely different psychological state than a user who hasn't opened the app in 6 months.
Oh, for sure.
Recency is often the single most powerful predictor of whether someone is about to churn, meaning, whether they're about to abandon your platform entirely.
Because if the recency number starts climbing from 1 day to 7 days to 30 days, the model sees the signal fading. Which brings us to pattern 2, frequency. How often does the user act? The SQL for this is essentially just count star. You are tallying up all their interactions.
Yes, and the underlying signal we are designing here is engagement. You might have a user who bought something yesterday, so their recency is great. But if their frequency is only 1 purchase a year, they're basically a tourist. Someone who logs in every single day to browse has a completely different persona.
And pattern 3 rounds it out, monetary value. How valuable is the user? The SQL code here is typically SUM amount, grouping all their purchases and adding up their total lifetime spending.
Right. The insight for the model here relies on a fundamental truth of commerce past spending is the best predictor of future value. If an ML pipeline needs to autonomously decide which 1,000 users get a premium promotional discount, it's going to heavily weight this monetary feature to ensure a return on investment.
Thinking about RFM, it's essentially just modeling a friendship.
Oh, I like that.
Yeah, like recency is when we last hung out, frequency is how often we text, and monetary is, well, maybe who picks up the check at dinner. But on a technical level, how do these three simple metrics, just recency, frequency, and monetary value, actually power massive systems like the recommendation engines at Amazon or Netflix? It seems almost too basic to drive a billion-dollar algorithm.
It seems basic, sure, but they power massive systems because they create incredibly dense multidimensional cohorts. A machine learning model doesn't inherently understand what a loyal customer is. But if it evaluates a user and sees a recency of 1 day, a frequency of 500 interactions, and a high monetary value, the model groups them in a mathematical space with other users who share that exact same RFM fingerprint. It's a highly efficient shorthand way to quantify complex human loyalty and predict what that group will do next.
So recency tells us when they were last here, frequency tells us how often, and monetary tells us their value. But absolute numbers like RFM have a massive blind spot, don't they? I mean, a user who spent $1,000 over 10 years looks identical to a user who spent $1,000 yesterday if we only look at lifetime monetary value. We need a way to create a fair comparison between wildly different users.
Exactly. And that limitation brings us to the next phase of Playbook: normalization, diversity, and ratios. This is where we start heavily refining those raw ingredients to give the model context.
Which introduces pattern 4 average behavior. Instead of just looking at total spending, we look at their average spend per interaction. The logic is basic. You take the SUM amount and divide it by the count star, total money divided by total purchases. But the playbook highlights a critical engineering trick here. If you're writing this in SQL, you don't just use a division symbol. You wrap the count in a function called NULEF.
This right here is a perfect example of thinking like an ML engineer instead of just a data analyst writing a one-off report.
How so?
Well, if we want average behavior, basic math says divide total spend by total purchases. But what happens to the automated pipeline if a brand new user enters the system and they have 0 purchases?
Oh, your count evaluates to 0. So you divide by 0, and your entire automated pipeline throws a fatal exception at 3 a.m.
Exactly. In mathematics, dividing by 0 is undefined. In a production machine learning pipeline, dividing by 0 causes the system to crash. The model fails to update, your daily recommendations don't generate, and the business loses money.
That sounds like a bad day at the office.
A terrible day. Using nullif, specifically nullif count star, 0, acts as a safety valve. It tells the database if the count is 0, replace it with a NLL, a blank value, instead of the literal number 0. The database knows it can't divide by a blank, so it just returns another blank, bypassing the math error entirely and keeping the pipeline running.
It's defensive programming built right into the SQL. I love that. Okay, pattern 5 tackles a different kind of context diversity. The SQL code for this uses count distinct product ID. Why is that distinct keyword so crucial for the model?
Let's look at the human behavior behind it. Imagine user A buys 10 identical plain white t-shirts. User B buys 1 white t-shirt, a pair of jeans, a winter jacket, and a baseball cap. If you only look at pattern 2 frequency, both users have exactly 10 purchased items. To a basic model, their engagement looks identical.
But their shopping habits are completely different. I mean, user A is stocking up on a uniform, user B is exploring the catalog.
Precisely. By using count distinct, you are counting the number of unique categories or items they interacted with. User A has a diversity score of 1. User B has a diversity score of 4. For a recommendation engine, diversity indicates broader interest. It's the golden rule in e-commerce. If a user exhibits high diversity, the algorithm can confidently recommend a wider variety of new, untested products to them without risking alienating them.
And building on that idea of refining numbers, pattern 9, which we're pulling forward because it fits this theme perfectly, is ratio features. The playbook calls these high signal features. A classic example is click-through rate, or CPR. You divide the number of clicks by the number of sessions. But if you were writing a query in Postgres right now to calculate CTR, you might think you were getting a clean decimal. But the playbook insists you must multiply the clicks by 1.0 before you divide. Why do we need that extra step?
Oh, this is one of those deep edge case secrets that separates beginners from professionals. In many SQL databases, if you divide an integer by an integer, say 9 clicks divided by 10 sessions, the database performs what is called integer division. It doesn't give you 0.9, it calculates the answer, chops off the decimal entirely, and rounds down to 0.
Wait, really? So a highly engaged user with a 90% click-through rate, the database just registers their CTR as 0.
Yes. Because 9 and 10 are whole numbers, it insists the result must be a whole number. So suddenly, your highly engaged user looks exactly the same to the ML model as a user who actually had 0 clicks. You have unintentionally blinded your model to their engagement.
That's wild.
By multiplying the clicks by 1.0 first, you force the database to treat the integer as a floating point decimal. 9 becomes 9.0. Then 9.0 divided by 10 correctly evaluates to 0.9. It is a tiny syntax trick, but it literally saves the entire predictive power of your feature.
One missing decimal point, and your model thinks your best customers are completely inactive. Wow. All right, so we have averages, diversity, and ratios. But all of these still represent a static snapshot of a user. Humans aren't static. Our behavior changes. How do we capture those shifts?
That brings us to the third phase time, trends and windows. Averages can actually lie to you if behavior changes suddenly. So we need pattern 6 trend and velocity, which is also known as change detection. The primary SQL concept here is the L function.
Conceptually, LAG is just looking in the rearview mirror, right?
Yeah.
You are comparing what a user did today with what they did yesterday, or the row just prior in the database.
That is exactly how to visualize it. And the machine learning insight here is that the rate of change often matters much more than the absolute value. This is the entire foundation of fraud detection. Fraud models rely on velocity.
Give me an example of how velocity catches what an absolute number misses.
Let's say a user typically spends $5 a day on coffee. Today, they spent $5,000 on electronics. If your feature just looks at the absolute value, $5,000, it might not trigger a severe flag because, plenty of wealthy users on the platform legitimately spend $5,000 a day.
Right, the number itself isn't necessarily bad.
Exactly. But if you use the AG function to look at the change between yesterday and today, the model sees a 100,000% spike in spend velocity overnight. The model doesn't care that 5,000 is a big number. It cares about the sudden, massive acceleration. That is what flags the behavior as anomalous.
It isn't how fast you're going, it's how hard you slammed on the gas pedal.
Got it.
Okay. Pattern 7 is the rolling window. The SQL code involves taking an average over the last, say, 7 rows, using a keyword like preceding. The insight is that we want to smooth out daily noise. But I have to push back here.
Oh, go for it.
How is a rolling window actually different from pattern 1, recency? They both just deal with recent time.
It's a really common point of confusion. Let's separate them. Recency answers a strict timestamp question. When did they last act? The answer is a duration. 3 days ago. A rolling window answers a behavioral question. What is their average vibe over the last week?
Duration versus vibe.
Exactly. Think about evaluating a stock price. Recency is just knowing the market closed at 5 p.m. yesterday. A rolling window is the 7-day moving average of that stock's price. It smooths out the daily spikes and dips to show you the current momentum. If a user usually buys healthy food, but in a 3-day rolling window they suddenly buy nothing but ice cream, the rolling window captures that temporary shift in their behavior without permanently overriding their long-term history.
That makes perfect sense. Recency is the rolling window is the what have you been up to lately.
Yeah.
And capping off this time section is pattern 10, time-based features. This uses code like extract day of week from a timestamp. Now, why do we need to do that? Why can't we just feed the raw timestamp directly into the model?
Because a raw timestamp is virtually useless to an algorithm. Think about a literal timestamp, like 2026-0330, 14.02.11. That exact second in time will never, ever happen again in the history of the universe. A machine learning model learns by finding repeating patterns. It cannot learn from an event that happens exactly once.
So by extracting Tuesday or hour 14, you are turning a unique, non-repeating timestamp into a cyclical pattern.
Exactly. Now, the model has a category it can match against historical behavior. A corporate software app will see legitimate, massive usage spikes on weekday mornings. If that exact same spike happens on a Sunday at 3 a.m., the model needs that extracted day of week feature to realize that this isn't normal growth. It's highly unusual and potentially a security threat.
Context is everything. Okay, moving to the next phase of the playbook categorization and the meta level. We have all these continuous numbers now, averages, lag percentages, rolling windows. But sometimes feeding an algorithm highly precise continuous numbers actually hurts its performance. Which brings us to pattern 8 binary flags, or discretization. The code here uses a case when statement. For example, case when total spent is greater than 2,000, then 1 else 0.
This is an incredibly powerful technique for reducing noise.
And I have to challenge this. If a user spends $2,000 and another user spends $2,001, and we use a binary flag to just label both of them as a 1 for high-value user, aren't we throwing away valuable precision? Why would we intentionally blind the model to the exact dollar amount?
It feels counterintuitive, but precision isn't always predictive. Sometimes precision is just noise. If you feed the model the raw numbers, it might burn vital computing power trying to figure out if that $1 difference between $2,000 and $2,001 represents a fundamentally different type of human behavior. We as engineers know it doesn't. They belong to the same behavioral cohort.
So the binary flag acts as a translator.
Exactly. Models often learn distinct categories much better than they learn from infinite continuous numbers. By discretizing the data, forcing those continuous numbers into a 1 or a 0, you are giving the model a clear, unambiguous signal. It drastically simplifies the mathematical learning process.
If we zoom out and look at the matrix of everything we've discussed, we arrive at what the playbook calls the meta-insight. You noted earlier that all 10 of these features fundamentally come from just 3 dimensions of data manipulation.
Yes. If you grasp this meta level, you don't just memorize 10 patterns. You can engineer anything. First, you have behavior, which we capture through aggregation using SQL functions like sum and count. Second, you have meaning, which we capture through transformation like our case when binary flags or our click-through ratios. And third, you have time, which we capture through window functions like lag or our rolling averages, aggregation, transformation, and window functions.
That's the holy trinity of SQL for machine learning. But the playbook also brings up a crucial conceptual point here, which I think is the most important mindset shift of the whole process. The idea that features are hypotheses. What does that mean in practice?
This is the exact moment a coder becomes an engineer. When you write a feature, say, calculating the 7-day rolling average of password resets, you are not just doing math. You are encoding a belief about human behavior. You're hypothesizing, I believe that a user's password reset frequency over the last 7 days is a strong predictor of their future engagement.
But what if your hypothesis is completely flawed? Let's say you assume a high count of password resets means they are highly engaged with the platform, when in reality, it just means they're trapped in a confusing, frustrating user interface loop.
And your model will be terrible. It will start recommending new products to users who are actively furious with your platform. And this highlights the most common mistake junior engineers make: copying blindly. They find a repository of SQL feature patterns online and just apply all of them to their dataset without thinking.
Right, just copy-pasting code.
Yeah, and blind pattern usage leads to weak, noisy models. You have to understand the specific human behavior on your specific platform before you apply the pattern. Better hypotheses create better models.
You can't just throw the whole spice rack into the soup and hope it tastes good. You have to understand what the ingredients do. Which brings us to a really tricky scenario. What happens when the playbook completely fails? Let's say a brand new user signs up for your app 10 seconds ago.
Oh, yeah.
They have 0 clicks, 0 recency, 0 frequency. There is no behavioral hypothesis to make.
Ugh, the cold start problem. It's the bane of every machine learning engineer's existence. How do you predict the behavior of a ghost? You can't use algor, you can't use county.
So how do you engineer features for someone who hasn't done anything yet?
You have to tie it back to the foundations of data architecture, which was actually covered in Lecture 1 of this series. When you have no event history, you must rely entirely on state features.
State features. Things like the user's age, their country of origin, the specific device they're using to sign up.
Exactly, who they are rather than what they have done. It's why every robust ML system requires both. State tables plus event tables equals a complete feature set. If the event table is completely empty for a new user, the pipeline falls back on the state table to make its initial predictions until that user starts generating enough event data to populate the behavioral features.
It's like making assumptions about the new kid in school based on what city they moved from, just until you actually get to know their real personality.
That's a great way to put it.
All right, so let's put this entire playbook together. Let's map out the final pipeline architecture for you listening. It flows like this. You start with your raw, indigestible data. Then you apply these SQL feature patterns we just discussed to translate that data into behavioral signals. You combine all those signals into a giant organized table called a feature matrix. And finally, you feed that matrix into the algorithm to train the model.
That is the complete life cycle, and it highlights the ultimate senior engineer insight from our source material. A beginner writes queries. They're just trying to get the syslect and join syntax right without an error. A professional uses patterns. They know how to solve common problems like calculating a CTR. But a senior engineer uses a playbook. They have a systemic, repeatable framework for translating human behavior into predictive signals.
A beginner writes queries. A professional uses patterns. A senior engineer uses a playbook. So what does this all mean for you, the listener? Now that you have these 10 reusable feature patterns, you intuitively understand the industry-standard RFM framework,
Yeah.
and you have a real ML feature toolbox, it is time to take the next step. It's time to test your real engineering thinking.
Because understanding the patterns conceptually is really only half the battle.
Exactly. Which is why I'm so excited to announce that next time we are diving into Bonus 2, the ML engineering interview drill. We're going to take everything you have learned today and throw it directly into the fire. We will cover tricky SQL edge cases, those terrifying NOL traps, insidious Joyan bugs, and the real-world interview scenarios that top tech companies use to weed out candidates.
It's going to be intense, but absolutely necessary. As the source material beautifully puts it, patterns make you capable. Handling edge cases makes you professional.
Handling edge cases makes you professional. I couldn't agree more. But before we wrap up, I wanted to leave you with one final thought to ponder. We spent this entire deep dive talking about how to build features that capture human behavior so that models can accurately predict what we want. But think about this. When these feature engineering patterns get so incredibly good and the models perfectly predict what you want to see, do the models start predicting your behavior, or do they actually start programming your behavior? Are you actively choosing what to click, or did the playbook choose for you? Ponder that next time your favorite app gives you a recommendation that feels just a little too accurate. We'll see you next time.